All right. So, all right, recapping what we've done up till now, right? So, I didn't include last Friday on this because we mostly dealt with some stuff related to homework 6. But basically, in terms of what we've done, right? We talked about how the different forms of the series relate to each other, right? And that gets to the formulas that Jacob was just asking about, right? These formulas here relate. If I have something in one form, I can relate it to another fairly straightforwardly, right? Then we talked about, okay, all the basic stuff for the Fourier series, right? Then we talked about sort of how to assemble it, looking at looking at the different formulas. Then we talked about how to figure out the coefficients for an arbitrary waveform. So today we're going to look at one more example of that, and then I'm kind of done with it. Basically, at that point, it's really just all calculus and algebra to calculate these things. There's all, if you I reference in here, the book talks about the 3 forms of the series, talks about the Fourier series representation. There's something like 72, 75 formulas in there, right? There's lots of stuff. I try to simplify that down into to getting you guys to understand the basic concept of this, which is to say, if I've got a periodic waveform, let me stop. I'm going to ask you this question. All right. What does it mean? What does this mean? What do these 3 formulas mean? In other words, so this gets back to one of my points of, all right, if I see you on the street in 10 years, you're not going to remember that f of t equals the sum from n equals negative infinity to infinity of alpha to the n times e to the j n omega naught t. You're not going to remember that. But what you might remember is what a Fourier series is. So what is a Fourier series? What am I talking about when so I have a sum of sine waves, but what specifically is a sum of sine waves? What's represented by that sum of sine waves? So that's why I'm glad I asked. Any periodic waveform can be represented as a sum of sine waves. So any periodic waveform. So a square wave is a periodic waveform. But we'll do an example today where I do this guy, right? That's a periodic waveform too. It repeats, and it's got impulses, right? So now you may look at that and we talk about where would I ever have that? So a square wave you can probably relate to because you've taken your digital classes, right? You have clocks, right? So those are real periodic waveforms. We have those all the time in power electronics, all right? We have them all kinds of places. That could, maybe not with the negative pulses, but that would represent, for instance, what we might be doing when we're sampling a signal. So what an A to D converter is doing, right? This would be a mathematical representation of what that's doing. So impulses are meaningful. But yeah, at the end of the day, that's basically what a Fourier series is to say that any periodic waveform can be represented as a sum of sines and cosines, which means that it can be represented also as a sum of a bunch of complex exponentials. What's the difference on this guy here, the third one, the complex exponentials? It goes from negative infinity to positive infinity, right? Because I got to include the negative frequencies, right? Because I got 2 vectors that it takes to represent the thing as opposed to 1. All right, so we talked about how to go through all that stuff. Now, where we ended up the other day was here, all right? Determine the coefficients for an arbitrary wave. And I basically defined out a 5-step process here where I said, all right, we got to figure out a suitable period over which to integrate. Got to figure out an equation for the function. Got to determine the alpha n values for the coefficients for n not equal to 0. We treat the n equal to 0 special. And then we relate to the other forms of the series. All right. Now, the reason I said we usually treat this one special is just primarily comes down to when I take an integral here, there's a 1 over n that kind of comes down sometimes, and that can be potentially problematic when I do that. So here's the alpha 0 right here, okay? How did I get from this formula here on the left to this one on the right? How did I get from here to here? It was a very simple thing to do. Yeah, there you go. I put in n equal to 0, right? What's that do? What happens to the e to the j negative j n omega naught t? It becomes 1. All right. What is this? We defined this the other day. I think Jaskin was the guy that knew what this was. What is this? It's what? It's it's the average value of x. And usually the way I write that is I with these brackets. All right. All right. So it's the average value of that function over a period. All right. So, all right, that's our process. Now we talked about all these kind of core definitions here, right? So we got our fundamental period, fundamental frequency, harmonic number, blah, blah, blah. All right. So let's do one more example. All right. So I've got this sort of thing here. All right. So this is a periodic waveform, and it's made up of impulses. Now let's remind ourselves about the impulses here. So I wrote numbers, a number here and a number here. What's that number and what's that number? It's the area. What's the height of those impulses? It's what? Infinity, right? The height is infinite. So what's true about the width of them? Yeah, basically 0. So they're infinitely tall, width of 0, area of 1. All right, and somehow you can have scaled areas, right? So we're gonna take a look at this guy here and try to build it. This is a periodic waveform, right? The definition of a periodic waveform is that x of t equals the same value a period later. Right, that's our definition. So in this case, that's true. What is capital T, the period? I don't need to do any greatest common divisors or anything here. I can look at this guy and figure out what it is. What's the period? What is it? 2, right? T equals 2. All right, because where it's basically here it is a t equal to 0, here it is a t equal to 2. The function repeats over that. Okay. So let's go through our process again. So step 1, identify a suitable period over which to integrate. So t equals 2, and the alpha n, we said 1 over t, integral from t to t plus capital T, x of t, e to the negative j n omega naught t, dt. Okay, so let's define some things for ourselves. What's omega naught in this case? 2 pi over t. That's what it always is, right? So it becomes what? Pi. All right. So I got that pi, and what's the units on that? No, we don't do units enough. Pi radius per second. Okay. All right. So I look at that thing here. What's a suitable period over which to integrate? Should I start at 0 and end at 2? I like starting at 0, right? Should I start at 0? It's a little weird to do that, right? Because if I said, all right, let's integrate from 0 to 2, what's the problem with that? Pulses are on the boundaries. It's not going to be kind of undefined. So what I'm going to do is I'm going to integrate from here to here. All right, basically I'm going to go from 0.5 to 2.5. Actually, no, I'm not going to do that. I don't want it because that's not the way I did it in my MATLAB. I'm going to do it from negative 0.5 to 1.5. All right, so I'm going to start here and end here. I'm still doing it over a period t. So notice, right, I'm doing it over a period, right? I'm going for over t equal to 2, but I'm starting so that I clearly just enclose those two impulses. All right, you guys follow that? I'll take, even if you get, you wouldn't really get a correct answer if you did it either, right? Because how many pulses would I be including? I would be including 1, 2, 3, right? So in this, I want to make sure that I'm including those 2 pulses. So here I get rid of any of that ambiguity by choosing something that does not, by choosing my boundaries so they don't align with the impulses themselves. All right. Now, step 2 was what? Step 2 was determine an equation for the function. Determine an equation for the function. So, and in particular, I need to get an equation for x of t, I guess, over the boundaries from negative 0.5 to 1.5. All right, so I got all fancy on t is an element of that range. All right, so what's that? What over that range there? How would I define x of t? Between negative 0.5 and 1.5, how would I define it? Well, I have two impulses over that range, right? So starts here, ends here. Two impulses are contained. Where are the impulses located? 0 and 1. All right. So how do I define the impulse at t equal to 0? Delta of t, 2 delta of t. Yep, because we said the area there is 2. Okay. And the other guy points downward. So it'd be negative 2. And it would be delta of t minus 1. Right? Because it's shifted over to t equal to 1. All right. So now I've got a function for that guy. All right. So step 3, if I go back to my steps, step 3 is to determine the alpha n coefficients for n not equal to 0. All right, so let's do that. All right, so we had defined here alpha n equals 1 over t negative 0.5 to 1.5 x of t times e to the negative j n omega naught t dt. Okay, and we figured, I'm going to leave it that way. We know that omega naught is equal to pi, but I'm going to leave it in terms of omega naught. Okay. What do I do? Yeah, first thing I gotta do is put the function in there. What is x of t, which we defined, right? So last time it was super simple because we had, so the example I did was a square wave, it was a constant over half of the period. In this case, it's the period is 2, so 1 over 2, negative 0.5 to 1.5, and I plug in x of t. X of t is 2 delta of t minus 2 delta of t minus 1 times e to the negative j n omega naught t dt. All right. This is actually, it's ugly, isn't it? It's actually pretty easy. Let me see, can I just try copy? See if this works. Nice, did. Okay, all right. Okay, there we go. All right, so likes me, but apparently Mikael doesn't like it. He won't. Yeah. All right. What's the how do I approach this guy? He's ugly, isn't he? Looks ugly. You got delta, all kinds of Greek. Look how much Greek is in there. We got all kinds of stuff going on. What do I do? I would, well, how would I throw that into MATLAB? I don't know how to. Maybe you guys are smarter than me with how to use the computer. You probably can find a way to do it. How did so it's easy. What do we know when we integrate with delta functions? Take the value. We have that sifting property. We take the value of the function at that location, right? So this guy's going to become 1/2 times 2 e to the negative j n omega naught times 0. I pull out the value of this function at t equal to 0, right? Then I do the same thing at what location? 1. So I say minus 2 times e to the negative j n omega naught times 1. And I'm done. All right, it's that simple. So what the heck did I just do? I think I clicked something there. All right. What do I do with that? Well, all right, I can plug it. Yeah, okay, at this point I can plug into MATLAB. I'm going to simplify that one more step. What's e to the negative j, blah, 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 0? 1, right? So I have apparently, and I got a 2 in each term, and I got a 1/2. So I'm going to say I've got 1 minus e to the negative j n omega naught. That now is my answer. And if I wanted to go a step further, I know what omega naught is. I could say this is 1 minus e to the negative j n pi. Right? Which if I wanted to really keep going and be a real math nerd on this, I could say, well, e to the j negative j n pi is equal to cosine of negative n pi plus j times what? Sine. So and you'd find some clever stuff that you could use at a nerd party to impress somebody that I think what's going to happen is the odd harmonics are going to disappear again. Right? But I know that the odd harmonics are going to disappear, but I don't really care. Right? This is good enough right here. All right. This I can now take and I can do something with this in MATLAB. So, all right. Step 3, we finished. Okay, step 4. Step 4 is this. And again, I wrote the areas here are 2 and 2. Step 4 was to figure out alpha 0, which is the average value of the waveform. So negative 0.5 to 1.5 x of t dt. All right. So I could do that integral. That integral will again look intimidating probably because I'll say it's 1/2 and there's a bunch of Greek stuff. Delta of 2 delta of t minus 2 delta of t minus 1 dt negative 0.5 to 1.5. Looks intimidating, but it's quite easy. Right? What's the integral of delta t? 1. Right? What's the integral of delta of t minus 1? 1. So it works out to be 1/2 times 2 minus 2 equals 0. Now again, I could have done that by just looking at this thing, right? Because if I look at that guy looks like over a single period, he has one pulse up with an area of 2, one pulse down with an area of 2. So it should be obvious that the area is 2 minus 2, right? Because there's as much above as there is below. Now, if I gave you, if this guy here had a height of 1, then you would say the area of this guy was, the average value of this would be 1, right? But that's not the case, right? We have this. But it's fairly straightforward to look at that, just do it by inspection. Because these numbers are areas. All right. The last step is, okay, where I ask you to say, all right, well, give me the alpha values, give me the A values, give me the B values, give me the C values, give me all that stuff. Okay. In the homework, I ask you to do that, right? I ask you and there'll be yet more of those on homework 8, right? Well, and in homework 8, you're going to get some fun stuff that you're going to be unhappy about. That's going to be like that. Why are you going to be unhappy about that? Well, this is going to take 3 integrals and it's going to be integration by parts, right? Yeah. So you have to be smart about how you do it. But I mean, basically, that's all it is. The process is the same, right? And you do an integration by parts, right? So it's not that hard, but it's going to be ugly, right? It's going to be an algebraic mess. There's no doubt about that. All right. When I do this, I want to make a couple of comments because you guys know once I have the alpha values, all right, how do I get the Cn values? How does C relate to A, alpha? Okay, so yeah, so C, the magnitude, all right, Cn, here we go. Cn over 2 is the magnitude of alpha n, right? And this is a magnitude. I'm going to be clear about that, right? And then we got an angle relationship. The angle relationship is the angle of alpha n is equal to phi n, right? Now, if you notice in the homework, in the prompt up at the top, I tell you to calculate C, N, A, and B, and phi But I don't ask you, if you look at the bottom, it doesn't actually look for phi. It's not solving for phi. Like that's, in other words, you're not graded on finding phi. You need to get it, but I don't check for it. And this, something I just want to talk about real quick. Let's say, for sake of argument, that alpha n works out to be 10 to the minus 19 plus j times 10 to the minus 18. What does that equal to? Any ideas? 0. Yeah, that's small. Now, numerically, in your calculations, you may get that. All right. This is the kind of problem that so sometimes sometimes you guys get stuff right that you shouldn't, because I'm overly generous on rounding, right? So when I look at this, let's think about it. If I took, so how would I get the angle of this number? Okay, yeah, I get the arctan of 10 to the minus 19 divided by 10 to the minus 18, which is the arctan of what? So I did that wrong. 10 to the minus 18 over 10 to the minus 19, right? It's imaginary over real, right? So that would be 10. This works out to be about 84 degrees or something like that. All right. I guess that could work. I could say e to the 0j 84 degrees, but it's 0, right? 0 has no, it's kind of unclear what angle would ever go with that. Numerically, depending on what computer you're using, you may get a completely different answer for what this thing is. So you could get some wild stuff, right? So rather than me trying to deal with that, I know that the angle is 0. So I don't, this is the numeric issues that sometimes come out. And I tend to give some generous rounding as a result of that. All right. So now what? So basically, that's what, if you notice, it doesn't grade you looking for the phi values. And that's why the phi can be pretty weird fairly easily. So, all right. So what I wanted to do was to figure out, well, how would I code this up in MATLAB? So here's how I coded this, right? So same thing like I did the other day. My code's almost exactly the same. I create an empty alpha n vector, right? Create this n complex vector, put in the period, figured out omega naught, created a t vector, and then here's where I calculate my alpha n values. So notice what I'm doing here, right? That's where I put in that formula that we just calculated, right? So in other words, this is, where is it? There it is. Put them together. Okay. So 1 minus e to the negative jn pi, which was pi was omega naught. So here it is, right? Is this relationship. Now let's say you don't like me concatenating. Well, what would I have done instead here? I would say this is k, right? And this is just simply 0, all right? And if you don't like me concatenating, then I would say this and this would be k, right? That should totally work fine too, all right? It may not like me doing this because I didn't give dimensions to that, but I think it's fine with that. All right, now what am I doing here? Yeah, this is where I'm making up the series. All right, so what's this thing gonna look like when I do it? Well, let's remind ourselves, what's the waveform look like? Looks like this, right? So what, am I gonna get impulses when I do this? What's an impulse gonna look like if I make an impulse? This what? Well, if I'm not lying and I'm making Fourier series, it better look like this. But in other words, it better look like that picture, right? But I mean, this is arrowheads, right? So pointing upwards, right? Is somehow this guy here times that's going to make arrowheads that point up and down? What's the waveform going to look like? Doesn't seem like it's going to make arrowheads, right? like a triangle wave. Well, it should look like this. So what do we say is true about these things? So we said their area in this case is 2. It should go off to infinity and it should be skinny, right? Is what it should look like. Now, initially I did this. What do I have here? I have n equal to 9, right? So I did 9 harmonics. So notice that means I went from -9 to 9 when I do the complex form of the series, right? So I'm going to do this. Run this guy. All right, I get that. Now that's got, so let's see, there's something going on here at t equal to 0 where it goes up, and there's something here at t equal 1 where it's going down. So it looks like it's got the right periodicity and everything, right? It's got all that stuff going on. Doesn't quite look like that. It is tall. I have this sort of weird stuff going on here. Let's keep going though. Let's take this to n equal to 100, right? So we do 100 harmonics and run it again. All right, now what's happened there? They got skinnier and they got taller, right? They're headed off towards infinity, right? Now there is this sort of weird behavior going on here. If I zoom in, yeah, there is this. What the heck is this? Well, something, if you remember that picture I showed of remember the square wave, and some of you have already done this probably in homework 7. The square wave had these little ears that it had when you tried to do the approximation of it. This is something called the Gibbs phenomenon. It always happens unless I truly include all infinite harmonics here. This behavior is going to occur. All right. So, but it looks, generally speaking, like what I would expect it to look like, right? It's got very large pulses that are very skinny. What happens if I go to when I include more harmonics? Because note, I'm not making the full Fourier series, because this guy, how many harmonics should I be including if I want to plot the real waveform? Infinite. I can't do that, right? I can only approximate. So I don't know. I'm gonna do something. I'll go to 200. I didn't try this. Let's see what it does. It should get bigger and skinnier. And it did. All right. And if I were to keep going, that's what would happen. It would get bigger and skinnier. And eventually these sort of what I call Gibbs phenomena would go away. All right. Question? How did I get to this graph? Yeah, like you were earlier, which is the sine waves. Well, let's say I do n equal 1, right? If I do n equal 1, what am I doing? I have 1 harmonic. If I have 1 harmonic, what am I going to see? A sine wave, a single sine wave, right? So if I do that, I get a single sine wave. That's the fundamental. So notice it's got the same frequency, all right? But looks nothing like that waveform. When I bring into a third harmonic, because I know that n equal 2, in fact, let's do that. N equal 2, I said this guy doesn't have any even harmonics. I know that for a fact, but I'm going to put that in there. It doesn't make a change because there isn't an even harmonic. If you were to go in and again plug in n equal to 0 here, that's you would see that the coefficient of that term is 0. So let me put in n equal 3. Now what I see is it changes to that. So you can see now that, okay, well, it's starting to get bigger at the right spots. Right? If I go to n equal 5, it's going to get even bigger at the right spots. And if I keep going like that, it gets bigger and bigger, and these sort of in-between pieces get smaller and smaller. To ever completely get rid of that garbage, you have to have the full infinite number of harmonics, which obviously I can't ask the computer to do. Right? I don't know how far I could add. What, I go to 200? I'll try 500 and see what it does. A million billion. Yeah. Let's see what it does. There you go. Right. So you can definitely see it got taller and skinnier there. All right. But the basic idea is there, and that's as far as we'll go with it, right? But so what you'll see in the homework is, again, like I drew that weird looking one, right, where it comes up and flattens off and goes down. That will start to that behavior where I said you get the Gibbs phenomenon, that ear behavior. If the function's smoother like this, it won't do that. You'll actually see that it'll look a lot better if it doesn't have a hard edge. All right. All right. That's it. I could keep doing examples, but I think you should know how to do that. It really gets down to just doing calculus. All right, at this point. So yeah. So the reason there's no even harmonics is right here. So I ended up with 1 minus e to the negative jn pi. So I expand that out, e to the negative jn pi, using Euler's identity, right? And so what that ends up with is, for any value of n that I would have here, sine of n times pi is always 0, right? For any integer value, that would always be 0. Cosine negative n pi is the same as cosine n pi. Cosine n pi, if n is equal to an even number, is equal to 1. If n is equal to an odd number, is equal to -1. So for an odd number, I'd have 1 minus 1 or 2, right? So the other way of looking at this guy is alternatively, if I went to the other form of the series, this guy would have bn values for n odd. Now, if you go beyond section 2 in the book, you'll find all sorts of properties of Fourier series. If I have what is called an oddly symmetric waveform like this, all right, in other words, so it based on the symmetry around the axis, it's always going to be the case that the even harmonics go away. Many waveforms you have in the real world have odd symmetry. And so you'll see that they tend to have odd harmonics. All right. If I were to show you, I think I showed it in the very first lecture, if I were to look at the voltage in that wall socket there, I would see that it has odd harmonics because of the odd symmetries that exist. There's all kinds of properties that one could show, and there's a whole Forrest Gump list of, like, there's all kinds of shrimp in the world, right, that you could go through, but they'll do that in 3111, I think. It's not interesting to me. What matters to me is you understand what a Fourier series is. All right, I know that you're not going to remember those properties. All right. That's it.